Hi, this is Mr. McGovern. Welcome to the 10th and last video in the series on Level 3 Circular Motion, where I'm going to go through a question from an exam paper, which is about circular motion. So the exam paper I've picked is 2020, so that might be one that you either want to practice after you've seen this or even practice before you've seen this. And I'm going to go through how I answer it, sort of invoking all the things I've taught you in the ways I've taught you in the videos beforehand. So in this question, Tom has a plane, which they give us the mass of 7.5 by 10 to the 4. If you're not okay with that, you should practice putting that into just normal kgs. So that would be 75,000 kgs. There are times when he flies horizontally in a straight line, and there are times when he has to take a circular path, such as when the angle is banked, the plane is banked at an angle to the horizontal. The diagrams represent the two situations. So we've got straight on and banking. Draw the force due to gravity and the lift force on the plane in the two situations below. Okay, so in the first one, where it's just going horizontally, probably at a constant speed, I'm going to draw the forces. It should be pretty obvious that those forces have to be balanced. We've got gravity going downwards and lift force going upwards. To show that they're equal to each other, I put the equal signs on them as well. That should be a pretty easy one. The banked one is turning in circular motion. So I know that the total force is going to be towards the center, and I have to make my two forces. There's only two forces on this plane because there's only gravity pulling it down and the lift from the air pushing it upwards. And lift is like a normal force where it goes always at perpendicular to the surface. So it goes off at the angle of the plane like that. I'm not sure in this case how big each one is compared to each other, but I'm not going to put them equals. And in the next question it asks me to explain how big they are, and I'll show you what I do then. Alright, so here is the next question. Compare the size of the force due to gravity and the lift force on the plane when Tom flies it horizontally in a straight line and when he flies it in a horizontal circle banked at an angle. Give reasons why they are similar or different. Numerical working is not necessary. But I would say before you start, even though it says compare, use as many diagrams as you can. A picture's worth 1,000 words. So in the first diagram, which I had before, I'm just describing what I saw, right? The diagram on the left. And what I saw is that the gravity force and lift force are equal. This gives a net force of 0 and describes constant velocity motion. Okay, so I've done my best to describe that they're equal and what that means when they're equal. When forces are equal and balanced, it means things are not accelerating. The second diagram I've redrawn here, it's going to be easier for me to talk about it once I've got my vector addition diagram. So I'm going to draw that in now. And the important thing is that I have a horizontal total force towards the center of the circle. So the plane will bank and turn in a circle, and that force at the top there, the total force, points towards the center. And so you can see that my lift force has to be bigger than my gravity force, because it has to cancel out the gravity force plus also kind of give it some sideways motion. So that's what I've said. In the second diagram, lift force must be bigger than gravity. This means that the net force is towards the center of the circular motion, as shown in my vector addition diagram. So even in an exam, I'd have the diagram drawn first, and then I'd just describe what I see. The lift force must be larger than gravity in order to cancel out gravity and to provide that plane with the horizontal or the sideways force, which is the total force. Okay, number C. On one occasion, Tom flies his plane in a circular path with the speed of 54 banked at an angle of 35. Calculate the radius of the circle that the plane describes. Explain your working for calculating the radius of the circular path the plane describes. Now, a diagram may assist your explanation. A couple of things. The diagram is going to be, hopefully, my vector addition diagram that I've got here. And my explanation, explain my working. If I've got very clear working, step by step, very easy to follow, that is the explanation. So I don't just throw numbers on the page. I've got either an explanation of what I'm using or a clear formula before I substitute the numbers in. That is a pretty clear explanation. So I need to find the radius, and the only thing with circular motion that I've got that has a radius in it is my total force formula. So I need to find the total force. How do I find that? Well, I'm thinking I'm going to use this diagram. So this will be part of my, I'd redraw it to make sure that the examiner knows. And it's at 35 degrees. So the next thing I need to do in that diagram is figure out where does that angle go? Where does that 35 degrees go? And from one of the earlier videos in this series, there's a couple of ways you can do it. If you're good enough with full-on maths, you can just prove where it goes. If you've done this enough, you kind of intuitively know where it goes. My little hint that I use is I redraw this whole situation as though it's a really, really small angle, like 5 degrees small, and see where it goes then, and just match it in the same place to this triangle here. So let's pretend it's on a very small angle. Here I've redrawn it. So I've got my lift force going nearly vertical, but not quite. Then my gravity force down. Put my vector addition diagram together the same way as the last time, and look for a really small angle. And here's my really small angle at the bottom there. So that means I know on my main diagram, my 35 degrees goes at the bottom, like that. All right. First thing we do with these triangles is we've got enough information to calculate the force of gravity. So I've done that there. 7.5 by 10 to the 4 times 9.8, I guess 1, but I've just got 9.80. Gives me some number. I'm going to put that on my triangle. I need to find the total force, which is on the opposite side, and now I've got the adjacent, so I can use tan. And tan 35 is opposite over adjacent. My total force is the opposite, so I rearrange this formula, and this is the number I get out for total force. 515,000 newtons. Alright, now I said that I needed to use this formula here. Now that I've got the total force, I can rearrange to find R. So this is me rearranged really quickly. Total force on the bottom, all the numbers in there, and I get out a number, 425 meters. That's definitely good enough for explaining my working, because I've very clearly shown what I'm doing, and I had a diagram to start with, and it shows the examiner I know what I'm talking about by using the vector addition diagram. Alright, and the last one, D, Tom then flies his plane at a height of 1.28 by 10 to the 4, so that's 12,000 meters above the surface of the Earth. Calculate the gravitational field strength, so that's little g. Normally, we have gravitational field strength, G equals 9.81. So as it gets higher and higher, that's going to change. So they've given us the mass of the Earth and the radius of the Earth. This kind of gives away what I'm going to do. But remember, when we use these things with the radius of the Earth, these calculations, we use it for things in orbit. But in anything when we're calculating strength of gravity, we've got to take the distance or the radius as the radius of Earth plus the height it is. So in this case, radius of Earth 6.37 by 10 to the 6. We've got to add on the 1.28 by 10 to the 4. I want to find little g, and the way I do that is I equate Newton's law from gravity to the simplified version we have, F equals m little g, where the little g is the gravitational field strength. So I equate those two because they both calculate force of gravity. I can simplify this because there's a little mass on both sides, and divide them, and so then I get little g, which is gravitational field strength, equals big G, which is your universal gravitational constant, which will be given to you at the start of the paper, times the mass of the Earth, mass of the thing in the middle, divided by radius, which is what we're talking about, those two distances added together. So I just basically put them all together. A key mistake here, or two key mistakes that people make. One is because you need to add these two distances on the bottom of the fraction, some people forget to put brackets in there, and things can get really nasty. So always, with this sort of calculation, put brackets on the bottom, just to be safe. I put brackets on the top as well, because I want to be extra safe. The second is people forget to put the squared in, so don't forget that either. And when I put that into my calculator, I get out 9.79, which is slightly less than 9.81, right? So the higher this person gets in their plane, gravity slowly gets less and less and less. So that's how I'd answer that question. I have rushed through this to some degree because I've already prepared the slides. In reality, it would take me a good 20-25 minutes to work through this. But you should have a go at practicing this yourself, and you can come back and get help from the video when you need it. So good luck out there, and thanks for watching this series.